Yeah, I think it's yours, Connor.
Sorry.
It's okay. Just wondering what it is. Is it like a laptop fan or something?
Didn't realize it typed so hard, like punching everything.
Wait, that's like you typing like 10,000 words a second. It's like
For group two that's just joined back as well, I was just saying the articles are really long, so it's fine if you didn't get to read through everything, but we'll just go through the gist of it. And Matthew's asked for requested his information from Netflix. I think you're on mute there, Matthew.
I've went through everything. I've confirmed my password and everything, and then they've said, "Oh, this process can take up to 30 days."
Is it data subject access support?
It'll be
Must be.
interesting to see what they have on you. You might be surprised.
Yeah, because when we were reading through that article, it was saying about it even takes into consideration like your ethnicity and whatnot. And I was like, I don't ever remember filling in anything to say that I was British or white or anything like that when I signed up, so I could be wrong.
Okay, great. So will we kick off then with group one? What you find out in Netflix?
So mainly, they try to keep customer engagement and subscriptions going through the thumbnails, and then just sort of it just explored sort of the intricacies and the challenges that they face doing that.
Were you surprised at how they actually changed the thumbnails based on the user, based on what they thought would appeal to you?
Like myself, I always knew that they had like, the thumbnails would try to maximize engagement, but this article helped me realize just down to the granular detail that it gets as well. It made me think of a lot of things that I've never considered before. So the amount of it surprised me. Like,
yeah, how personalized they are. I'll open it here for group one just to show you guys. Can you see that screen there, how Netflix uses AI?
Not at the moment.
not yet.
No?
No.
Let's see. That any better?
Yep.
Yeah, that's it. Okay,
Yeah.
so yeah, just what we were saying there. So these thumbnails, for each series or each film, there's hundreds of thumbnails that Netflix can choose to use. So there's just 9 for Stranger Things that they can choose to use, all for the same program. So Netflix takes into account your individual preferences, what you've clicked on before. It's careful. It's careful that it doesn't, that it can differentiate that just because you liked A Bug's Life, you doesn't mean necessarily you'd like The Human Centipede. You don't have an addiction to bugs or anything like that. But yeah, it just goes through that one user could see The Godfather like this, and that might appeal to them if they've previously clicked on a film that has, a male as the main character or something like that. Whereas somebody who might like romance will get shown The Godfather as this thumbnail. So all the thumbnails are personalized, and like I say, they have hundreds to choose between. So there's another one. If you like romance, then it'll show you this thumbnail for Riverdale. If you're more inclined to thrillers, then you'll get shown this thumbnail. It went through a bit of bias as well. So yeah, I think we talked about ethnicity there. So if you prefer, a certain if you've watched a certain race or something like that, based on your ethnic priorities or preferences, then it can sometimes lead to bias, and that's something that Netflix has been called out on. I think these two characters on the right-hand side, they weren't actually even main characters in the film, but just because it tried to get so personal and so detailed, it actually just showed these characters as a thumbnail for one user, but it might not have necessarily reflected what the film was about. So that's a form of bias. So yeah, that just goes through the rest of them there, but definitely an interesting article. Was there anything, Team One, that you guys were surprised about? Surprised to learn? Or I know obviously, Matthew, you've requested a copy of your information now, so you're interested in what they hold about you.
So it's a business case too. Something when you read on down, it talks about, you know, further developments or enhancements. You know, what's going to be most productive: voice recognition versus voice output, or keeping it simple, text in versus text output. You know, it has to be a real strong business case and evidence there's going to be a return on the investment.
Yep, 100%. So before any of these companies will invest in machine learning or more tech, then they will always see if there's a business case for it. But definitely an interesting read. I hope you found it interesting.
It's just something I was wondering though, how useful is it to show, like for example, the Godfather one there?
Yeah.
How useful is it to show someone, oh, there's romance in this? Because of all the genres the Godfather's in, romance wouldn't have been one I would have put down. You know what I mean? So you could get someone who's watching a 3-hour film, he might not end up liking it.
Yeah, that's so true. Yep, that's right. So what's the point in personalizing them? What's the point in trying to target an audience that previously didn't like that genre?
Yeah.
What I'd say is it doesn't just show you pictures, but if you're not going to be interested in The Godfather because you only like romance, it's not going to show you The Godfather in the first place, rather than show you stuff that you're not interested in, but with a picture that you might like. That's where it takes into account both of those.
Yeah. Yeah, I get what you mean. So first of all, it'll prioritize films that you might be interested in, but afterwards then it'll actually go to a scene in the movie that is specific to what your interests are, maybe.
That makes sense, yeah. And then the other thing I was wondering is, I know like if actors are featured on like posters and things like that, you know, they're advertising the film, they get paid more. So I wonder if that affects like the Netflix deals, because as you say, like those two black characters, they were only like minor in the film. So I wonder, do they end up getting like paid more because they're being used to advertise on Netflix?
Yeah, it would definitely be interesting to find out.
I don't think so, because was there not a whole big thing with Scarlett Johansson and Black Widow? Because her salary was dependent on like box office sales, but they put it on Disney Plus and charged people, so she didn't get any money from Disney Plus.
Yeah,
They've resolved that now, so they have.
Have
they?
Yeah.
Under the table, was it?
Not sure.
Well, she's got another movie planned with them in the near future, so obviously she got some sort of settlement.
Yeah, but they reckon they did her out of like 50 million in wages.
Well, that's what she claims, but as for whether or not that's the case, who knows?
She's happy either way.
Yeah.
All right, brilliant. Grip 2, what did you find on Duolingo?
They monitor everything, like down to what word you know. They're going to guess how fast you're going to forget it. They're going to know what's the best message to send you so that you'll open the app. Yeah.
Yeah, so it's almost so personalized that you get into a position like Matthew, and you wonder what kind of information do they hold on you, and request a copy of it all. So it is really personalized, and you can see how complex and how technical that the algorithms that they use are, because they can, you know, the wording of the message, like you say, Victoria, the wording of the message that they send you, that the notification pops up on your phone, they know how to write it, they know what time to send it to you, to get you to go on to their app.
Also, they know how fast you're going to forget a word. So it basically tells you how stupid you are.
Yeah, so there's always two sides of, you know, using this artificial intelligence and using your information. Some people like it because they find it easier, more convenient, and you know, it makes their learning experience more efficient, or their experience with technology more efficient. But then on the other foot, there's people who, you know, don't want to share all that information. So yeah, there's definitely two sides of the coin there. It's good that the technology's there, but maybe asking the user first, can they make use of it?
You can obviously see a dark side to it too. You know, you can just imagine what Paddy Power or Bet365 or one of those could do with this sort of information.
Oh,
I work for
definitely.
Paddy Power, and I'll tell you right now, if they are letting you place bets with them, they have made money off you. I worked in their online customer service. If you take money off of them, they will cut down on what you're allowed to bet to. So we had a guy, and he
Stop
wanted
giving you free
10,000
bets.
pounds. Yep. And he was only allowed to put 10p on for bets after that. Wasn't allowed to do a pound accumulator no more. 10p.
That's crazy. And that's all probably alerts in the background, like you and customer service get told about that, but I'm sure it's all like AI that does that, you know, detects patterns.
Yeah, like if they were using a chatbot and stuff, yeah, it would definitely be. Yeah, it's crazy. There's a lot of sad stories you could get, and I think, yeah, knowing so much detail about people and being able to trigger them so easy to come onto the app could be very, very dangerous. So I don't know. There has to be like ethical issues with that.
Yeah, and this is why responsible AI is so important as well. And like I say, all the big companies, all the big tech companies, and you know, we looked at the big four and stuff last week as well. They do have a set of principles that they abide by, the responsible AI principles. But really, every company that uses AI should have that enforced. But it's just the regulation and the legislation is just catching up with how fast the technology is actually evolving. But yeah, definitely two interesting articles. So back to the slides. So I'm sure everybody's heard of the term big data before, and big data is just what it says in the tin. It's just large data sets, large populations of data, working with loads of information, where it would take a human lots and lots of time and manpower to go through and identify trends, identify patterns. In the case of, we said there, Paddy Power, identify how many winners have there been, how much have they won, and you know, adjusting their credit limits accordingly. So, yeah, you back?
I showed you a power up there.
Oh, did you? Did you share it?
It's called ImageML.
Right. Yeah.
And it's designed to recognize McDonald's logos.
Nice.
Right.
Yeah.
So if you get a few McDonald's pictures, ones with the logo, and there's some of them maybe more obscure pictures. I'll send you a few pictures as well.
Do you need a login or anything, or is it already up and running? You can just go in and
your emails and your Office 365 apps, right?
Yeah.
Click on Power Apps and share it with me or something like that, and it should be there.
Happy days.
All right.
Happy days. Yeah.
It should link. It's shared. It should link from your email as well.
Right. Perfect.
So if you do the quick test, rather than running a quick test and drop an image in, it'll find the McDonald's logo and give you a percentage certainty.
Oh, happy days.
Quite good, actually.
Sounds good.
The only thing about it is it's 30-day trial.
Right.
So if you are going to use it for your assessment.
Oh, it's better to introduce it maybe later, a bit later.
Show them that the haven't not activated yet.
Ah, right, I get you, yeah.
And then whenever the assessment goes out, they can use it if they want to, Kaggle or Teach One or.
We'll just give them the option, yeah.
Yes, 30 days trial of this. Not using it yet.
Okay, sounds good. Cheers, Chef.
I've got a few practice images, but send them.
Brilliant, thanks. Okay, so big data. So like we said, an increase in data or more observations leads to an increase in the machine learning model's predictive ability and accuracy. So you would have seen there when we went through the Google machine learning model. So the more dogs you had, or in Victoria's case, you know, the more black rabbits you uploaded, then the more accurate the model was able to be. So machine learning algorithms find natural patterns in data that help make better decisions and predictions. So like I say, we're not all Rain Man. We can't look at, a big spreadsheet full of data, numbers and figures and straight away make patterns, whereas a computer can. In the modern world of big data, there are so many opportunities to use machine learning. Like we said, across all industries, machine learning can be used. So we looked at Netflix, we looked at Duolingo, we talked briefly there about Paddy Power, we talked about credit risk models, which can be used across the financial sector. And machine learning is useful for complex tasks or tasks involving large amount of data and variables. So let me know if you can't hear this volume. I might have to just change those settings again. Is that playing okay?
No sounds.
No sounds, no worries. Let me just unshare and share again.
Our ability to learn and get better at tasks through experience is part of being human. When we're born, we know almost nothing and can do almost nothing for ourselves. But soon, we're learning and becoming more capable every day. But did you know that computers can do the same? Machine learning brings together statistics and computer science to enable computers to learn how to do a given task without being programmed to do so. Just as your brain uses experience to improve at a task, so can computers. Say you need a computer that can tell the difference between a picture of a dog and a picture of a cat. You could begin by feeding it images and telling it, this one's a dog, that one's a cat. A computer programmed to learn will seek statistical patterns within the data that will enable it to recognise a cat or a dog in the future. It might figure out on its own that cats have shorter noses and that dogs come in a larger variety of sizes, and then represent that information numerically, organising it in space. But, crucially, it's the computer, not the programmer, that identifies those patterns and establishes the algorithm by which future data will be sorted. One example of a simple yet highly effective algorithm is to find the optimal line separating cats from dogs. When the computer sees a new picture, it checks which side of the line it falls on and then says either cat or dog. But of course there can be mistakes. The more data the computer receives, the more finely tuned its algorithm becomes, and the more accurate it can be in its predictions. Machine learning is already widely applied. It's the technology behind facial recognition, text and speech recognition, spam filters on your inbox, online shopping or viewing recommendations, credit card fraud detection, and so much more. At the University of Oxford, machine learning researchers are combining statistics and computer science to build algorithms that can solve more complex problems more efficiently, using less computing power. From medical diagnoses to social media, the potential of machine learning to transform our world is truly mind-blowing. To find out more about machine learning, visit oxfordsparks.ox.ac.uk, follow us on Twitter and find us on Facebook.
Okay, so that went through exactly what you said this morning, building the model between the cat and the dog. So for the purpose of this course, we don't have to actually go into the code behind, we don't have to build the algorithm in coding form. We don't have to be developers. We don't have to do any of that. But we do have to understand which components the model's looking at. So we'll go through that for the rest of today. The first thing that the model will look for is features. So features are also X values. So X values are known values and they're what you input to the model. So if you think of say an ice cream shop. So an ice cream shop is trying to predict how many ice creams it'll sell on a given day. Now, what determines how many ice creams the ice cream shop will sell? A big factor will be weather. So, if the higher the temperature, the more ice creams it's likely to sell. Another one might be season. So whether it's summer, spring, autumn or winter. If it's summer or spring, it's more like, or autumn, it's more likely to sell. Another fact could be how many hours a day the shop stays open. Another one could be what's the population surrounding the location that the shop is based. So loads and loads of factors feed into a model, and they're called features. So features are what the model is built upon. So a feature, actually, all the features combined creates the algorithm then. So they're known values and they're input to the models. So here on the right hand side, we have, I think this is retail. Yeah, so the price of property, I think that's $1.29 million. So based on the size of the property, based on how many bedrooms it has, how many bathrooms it has, and its zip code, which basically takes into account its location, all those features combined feed into a model, and the model gives out what price the house is likely to sell at. So the labels are the Y values. They're the unknown values that we're trying to predict, and they're the values that are output from the model. So it's really important to differentiate between features and labels. Features are the values that we already know that go on to build the model, and labels are the Y values that are output. So your label in the cat, dog, or rabbit situation, the label would be cat, dog, or rabbit. The features that the model used based on how many images that you put in, it could be the pointed ears for the cat, the long tail, the smaller size. A dog could have been, you know, they're a more diverse range of sizes, floppy ears, softer looking features. All those features feed into the model, and then your model then output the label, whether it was a cat or a dog or a rabbit. So two terms that we'll use as well, supervised learning and unsupervised learning. So supervised learning is just what we've, the two models that we've looked at already. So supervised models have labels. So supervised models have predefined labels. So in the cat or dog situation, we uploaded loads of pictures of a cat and we give it the label cat. We uploaded pictures of a dog, give it the label dog. So we uploaded all them, and their labels were cat or dog. And then our model then was able to predict, based on a new image, our model was able to predict whether that's a cat or whether that's a dog. It was able to give that a label. Unsupervised learning, on the other hand, does not have predefined labels. So we'll come across unsupervised learning more next week when we look at clustering model. So unsupervised models do not have Y values, they do not have labels. So we just get a whole bunch of data and upload it, and the model kind of figures out itself. It breaks the data into clusters and it outputs clusters, but there's not necessarily a label involved. Like I say, this might sound a bit abstract at the minute because we haven't got hands-on with clustering models, but just so that you know that term, unsupervised learning, it's just when a model has no Y values. So we just look here at how the model processes data in a supervised learning environment and an unsupervised learning environment. So we're given the raw data in a supervised learning environment. We train the model. We say this picture is a dog or this picture is a cat. That's training the model. The algorithm is then built, and it was built in our case by Google. And we have the trained model, and we upload new data, and the model gives out whether it's a cat, a dog, or a rabbit. In unsupervised learning, we don't train the model. We just put lots of data into a model. An algorithm is actually built around that data. So in clustering, and like I say, we'll go into more detail in clustering next week, but we can just say we want this data divided into two groups, in which case, if it's a picture of cats and dogs, then it might automatically say, all right, cats and dogs, those are the two groups. We can specify instead if we want three groups. In that case, depending on how many colors we've uploaded, it could say three groups, one of black animals, one of white animals, one of brown animals. So we just identify how many groups we want, how many clusters we want, and the model does all that for us. So you don't know what features it's going to use to differentiate. All we do is tell the model how many features we want, and it groups the data based on that.
So does that mean, sorry, just the
Yeah, go
the
ahead.
Amazon one and stuff, were they unsupervised learning then? Or was it a bad like spread of data from supervised learning?
What was that, the Amazon one?
Yeah, but for example, what would, yeah.
Which Amazon example are you talking about, just so that I'm sure?
The hiring one.
Oh, the hiring one. Yeah, so whether it was, yeah, males or females. I think that would have been supervised because there was an output, so it would have said interview or not interview maybe. But it depends. I'm not sure how that model was built, but it could have well been, it might have just grouped them into different groups. But I think because they wanted the output hiring or interview and not interview, it probably was supervised. Unsupervised is when we don't know what output we're looking for. And like I say, it's very abstract now. When we look at clustering next week, it'll become more clear. But unsupervised basically means that we're not building a model. We don't know what we're actually looking for. We just want this algorithm, this machine, to split the data in some way. We want it to basically structure the data in some way, and whether that's based on color, or whether that's based on size, or whether that's based on another different feature, that's for the machine to decide. But we have a lot less control over unsupervised models because we can't determine what features will be used. Yeah, but like I say, it will become clear. It's just getting to terms with the terminology, supervised and unsupervised at this stage. And supervised is where we know what the output is. We know what we want. Unsupervised is we have no idea what we're looking for. We just want the data to be structured some way or another, if that makes sense.
Yeah, thank you.
So 3 types of machine learning models. There's the 3 main types we'll look at in this course are regression, classification, and clustering. We'll look at regression in detail today, and next week we'll look into classification and clustering models. So we'll take a break now. We'll take a break until 11:15, and then we'll come back and start with regression models. I'll be here if anybody wants to chat or has any questions or anything, but yeah, feel free to take a break now for 15 minutes.
All right, cheers.
Thanks. Okay, thank you.
Thank you.
Right, folks, is everybody back?
Yep.
Yep.
Yeah, okay, all good, cool. I'll just share the presentation again. Just to let you know, for the assignment, for the first piece of coursework, we'll actually be building a model or maybe 2 models. So this stuff is all really useful, you know, getting insight into the Google AI model builder and things like that. That could be one of the resources that you want to use, but I'll show you a couple more next week as well.
When does the first assignment get released?
Probably in about 2 weeks, maybe, probably around week 4. Probably around then. It's just going through validation at the minute. So the first assignment, yeah, so I think I touched on it with you last week, but we didn't go into detail because it was still getting, we were still trying to work out what was feasible remotely. So the first assignment will be a piece of coursework. You'll have a few weeks to do it. And it'll be 50% of your overall grade for this module. So 50% piece of coursework, and it'll be, I think, 2 sections, maybe building 2 different models. The second assignment or a test, it'll be a test, but we'll see how we can kind of work it out. So the second part's a test, that'll be later on in the module. That'll be 50% as well. The first section will be multiple choice, and the second section will be long written answers. So kind of like 2 case studies or something like that, with parts to it.
Okay, thanks.
Yeah, I'll let you know more details as soon as we hear back from where they're up to and getting validated and everything. We'll go through more details. Okay, so regression model. So regression models are the main form of machine learning models. So the most popular, and for the rest of the session, we'll talk about regression models. They do take a wee bit longer than the classification and clustering models to go through, but it's really good to understand the methodology behind them. So regression models are used to predict a numeric label based on an item's features. So numeric is the key word here. So that could be predicting somebody's salary based on their age, their years of experience, their job title, something like that. It could be used to predict, you know, what temperature it'll be tomorrow. It could be used to predict anything that has a numeric value. So we're looking for a discrete numeric value. That's what we're looking at from a regression model. The output should be numeric. So regression models have features, which are X values, and labels, which are Y values, meaning they're an example of supervised machine learning. Because they have these Y values, they're supervised machine learning. So if you look at this graph, X will be the features and Y will be the labels. So based on the feature you give, Y will be the output, Y will be the label. So if you look at 2 real life examples here, so ice cream sales and temperature, we touched on this one earlier. So based on the temperature, it goes 0 to 40. So based, I don't know where they're based, but based on the temperature, the revenue from an ice cream shop is shown here. So this is just based on one variable. You can have a lot more features, but just based on one feature, the temperature, this is how much revenue they bring in that day. So you can see the higher the temperature, the better the weather, the more sales the ice cream shop will get. Another one here is salary based on years experience. So based on, if you have more years experience, you're more likely to get a higher salary. Now there's something called anomalies, or sometimes they're called outliers, and they just lie outside of the general trend of the data. That could be for several reasons. It could be, you know, it could be a mistake. It could be a mistake in recording the data. It could be just that they're a one-off case. It could be, in this case, so it's somebody who's well experienced, but they're not getting a salary to reflect that. So maybe they've recently changed jobs. Maybe they've went into a different sector and had to start from the bottom up, or maybe they've started out on their own, self-employed, and, you know, they're not giving themselves much of a salary. So there could be reasons to explain that as well. So this black dotted line is called a line of best fit, and that just tries to model your data, all the data points that you have. So this is the model here plotted. And if this model now was given a feature of, say, somebody has 5 years experience, they'll use this black line. So they'll go up 5 years and say, okay, I expect that person to be on 70K. If the feature that is input to the model is 10 years, then they'll go to 10 years, go to the black dotted line and say, okay, I expect this person to be on 105K a year. So that's how these graphs are read. So these are scatter graphs, scatter plots, and they're really good for plotting regression models. And yeah, an anomaly can also be called an outlier. So anomaly detection or outlier detection.
Can I ask you a question on that? Sorry.
Sure, yeah.
So in both of those instances, it's basically comparing one X to one Y.
Yeah.
But what if you're getting, so let's say you're looking for the first one, you're looking for ice cream revenue, but you're getting temperature and time of the year, or you're given multiple X values.
Yeah.
How would that then look on a graph like this?
If it's a multiple regression model, then it won't be so simple to plot. So yeah, that's a good point. These graphs are only really good visually if you have one feature. So yeah, that's a really good point. So there's a wee bit of a case study here. So Bicycles is a bike rental store which loans out bikes in the city. The business would like a model built which can make use of their historic data to predict the daily rental demand to allow for inventory planning and staff rota planning. So they want to predict basically on a given day how many bikes will they be able to loan out. So Bicycles have data for the past 18 months, including the amount of bikes they've rented out each day. And we've also been able to source historic weather data. So which features would you consider to be relevant in the model build? Break into groups to discuss. Okay, I've made 4 groups here on teams, group 1, 2, 3, and 4. I'll just do it in alphabetical order. So let me see. So if Connor, Daniel, David go into group 1, and then James, Joshua, Matthew Robb, and group 2. Matthew Ward, Michelle, and Nathan into group 3. Ronan, Thomas, and Victoria into group 4. And we'll just discuss that for, give it 10 minutes. So we'll come back at 11:35, and you can let everybody know what features you think would be relevant in predicting the amount of bikes loaned out. Okay, I'll just write in the chat here, 11:35, we'll come back. Right, I think that's everybody back. How do we all get on, folks?
Yeah, good. We came up with a few ideas of correlations between busyness and rentals.
Brilliant. Okay, so we'll start with group 1. So that was Connor, Daniel, and David. If you just want to go ahead and tell us what features you thought would be important in predicting the sale or the sales for the bike shop.
Okay, so we correlated busyness with the likes of weekdays, so potentially Mondays to Fridays being busiest, considering it's when most people tend to work. Correlation with season/weather, so potentially busier in the summer/spring versus the autumn and winter, and probably busier on sunnier days versus wet, cold days. Potentially related to events as well, so if there's anything special going on, there might be more rentals, so you may want to put on more staff and have more bikes available, for particular events.
Yep.
Time of day, so unlikely to rent bikes at night, and most likely to do it during the day, and maybe even morning time /afternoon, early afternoon. And then we also talked about the potential for repeat customers and just monitoring their trend going forward. So you might have somebody who rents a bike on specific days of the week, and then you can plan for them moving forward as a prediction.
Yeah, so even include those personalized things that you know, those patterns that you know are likely to reoccur and happen again. Brilliant. That was plenty there. Some really good ones as well. I like the fact that you thought about the day of the week. So depending on the day of the week, they might have more or less sales, and that could be, I suppose that could be depending on where the bike shop was based. You know, if they were based in the city and they were used by commuters, then definitely Monday to Friday they'd be a lot busier. Or if they were based out in the countryside and people went there at weekends, then maybe at the weekend and maybe on bank holidays they would be much busier. So all really good features there.
That's actually a good point. I hadn't considered location of bike store, but yeah, I guess that does correlate as well based on where they're located. I just automatically thought they would be servicing city centre, but it doesn't necessarily have to be. So
yeah, I think really good points. Group 2.
Yeah, I assumed they were going to be like mountain bike kind of bikes. So that's
so you thought the
interesting.
opposite. You thought that it might have been busier at weekends.
Yeah, weekends, and you might get someone who said weekdays. I was like, really?
Well,
So it's just getting all that information.
It is in the study.
Yeah, on the PowerPoint it says, let's say.
Well, that's my bad.
But no, definitely location is another really good one, and it's just about finding out as much as you can about the situation to include the features and include them in a relevant way as well. Group 2, have you anything to add? Group 1, Daniel, you give loads there from Group 1. Is there anything else to add, Group 2?
Yeah, we were going to measure the type of bikes that were sold, then you can graph that against, like maybe certain days of the week or events or things like that there as well. And also we correlate possibly with location. So mountain bikes might be in a more rural store, and then I don't know what the other type of bike is, but that one might be more popular in the urban centres,
Yeah, no, that's a really good one. And the fact that you mentioned events as well. So that could look like an anomaly in the data. If there was a one-day event or something like that, where loads of people were about, and the bike shop would experience, a significant increase on that day, or a holiday or things like that. Group 3, anything for you guys to add?
For us, we had maintenance and repairs. So if a bike was broken, if somebody had crashed it, or if somebody had stolen the bike, then you need to take that into account. Then also age. Age of people using the bikes, because if you have, say, a family that are coming in for tourism, then you need to take into account that sort of over the summer months where you've got a lot of family holidays, then you'd need more children's bikes as well.
Definitely, that's really good. I think we said on the slides as well, it was for inventory planning for managing the inventory. So no, that's a really good point. Differentiating between how many children's bikes you need, how many mountain bikes you need, and different categories and different types of bikes. are for different categories of individuals. So no, that was a really good point as well. Group 4, we're gonna have to start mixing these up in these scenarios, because I think there's so much said already. Group 4, is there anything else that you guys thought about that you'd like to add?
In terms of actual numerical data, things like rainfall and temperature could be used to accurately plot graphs. And I think as well, because of the fact that it's only 18 months, looking at the time of year might be a bit less reliable, because you might only have one instance of specific months, and you might have anomalies there.
Yeah, definitely. And I mean, in real life, the past 18 months has been, you know, a lockdown for a lot of the time. So it's always useful. Machines can only take you so far, but it's always useful to have that subjective overlay, because what's happened the past 18 months in most industries, I suppose, might not necessarily be, you know, the trends that will be followed in the next 18 months. Just because we had COVID, we had the lockdowns, we had that massive anomaly of that event. So yeah, all features like that. But no, that was super. So if you were building a model yourself, in the coursework, like I say, you will be building a model or two yourself. It's really useful to know what features are relevant, what features you would include. And obviously, I don't think anybody was biased there at all. So just make sure that, you know, the features are there for a reason, nothing's biased. Okay, so regression methodology. So this is a big bit of theory here. So in linear regression, we train the machine using known features, so your X values, and known labels. That's the outputs, the Y values. We train the machine based on, we give it all these features and say, on this day, at this temperature, there was an event or there wasn't an event, you know, in a bike shop located wherever, with a rainfall of 10 millimeters, a rainfall of 8 millimeters. All those features we include, and for each day we say, these were the features on this day, and this was the output. This was the amount of bikes that were loaned out on that day. So it's fitting all those features, the combination of those features, and giving them different weightings. So maybe temperature might be highly weighted, you know, it might be a significant feature into the model, but something else such as, you know, the difference between it being a Tuesday and a Wednesday, the day of the week, in that case, might not be so significant. So you might give that less weighting. You could also make new features. So you could create features. So instead of saying Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, you could say one feature is called weekday. And you could say, if it is a weekday, give it a 1. If it's not a weekday, give it a 0. That's your new feature. That's creating a feature. So we'll learn to create features, fit features, all those different combinations. And what the model does, it takes in all those features and gives them different weightings, depending on how much they influence the output. So once the training is complete, the machine can predict labels for new and unknown items. So just like we seen this morning when we were looking at those cats and dogs and rabbits, the model was trained based on the information you give it. It selected, you know, different features such as the ears, the size, the tail, things like that. And based on that, the machine can predict labels for new and unknown items. So then when you upload a brand new image it hasn't seen before, and then it'll select them, you know, which is the best. Because we're looking at regression, it wouldn't be classed into a cat, dog, or rabbit. Because we're looking at regression, it'll actually give you a numeric output. So that could be the temperature, predicting the temperature for tomorrow, predicting the sales that, you know, a shop around the corner will have this week, predicting, like we've seen in the previous examples, ice cream sales, salaries, things like that. So predicting a numeric output. So the mathematical equation, Y is the predicted label, X is the features, and F is just the function. So if you've ever seen Y equals F of X is just the model. It's just the function. It's just instead of writing out the whole entire algorithm or model, f of x just accounts for the model. So the label is based on the model, based on f of x. So in the bike rental example, the details about day of the week weather example are x, they're all the features. The number of rentals of the day, the output that we're looking for is y, and the f is the function that calculates the number of rentals based on the information. So like I say, f of x is just the model. F of x is applying the model to x to get out your y value. So once we have all of our data, so say we have, what was it there, 180 days of data. So we'll want to train a model, but we won't want to use all of that data because we'll want to keep some of it aside so that we can test and see how good our model is before we deploy it. So if we have, say we have 100 observations, so 100 days of data, we'll use, the standard is about 70 to 80% of it we use to train and build a model. So we'll randomize that data. So we'll just make sure, so in that last example, it was 180 days, you know, one after the other. And you can obviously get, you know, you get skewed data because if we start in the 1st of January, it's obviously winter, it's cold, and you get very little bike sales. And as it goes into the summer, then you get more and more. So if we just took the first, 100 observations there, it would all be the winter months and it would be skewed. And then if we're trying to predict then, you know, going into the summer, our model wouldn't necessarily be fit for purpose. It would be undervaluing. So the first thing we always do is randomize the data just to make sure that it's not based on date, that it's not by any way sequenced. So the first thing we always do when getting a data set is we randomize the data. So we split it by rows, and basically what that means is we just take a full row of data. We take, on a given day, we take all of its features and its output, its y value, its label. We take all of that data. We just take that row of data and extract it. So we randomize it, we split it by rows. Like I say, the standard training test split is 80-20 or 70-30, but it depends on the volume of data that we have. So if you only have a small number of data points, then you'll have less to do that with. You know, you won't be able to do you might not be able to do the 80-20 or the 70-30, but yeah, the standard, like I say, in your coursework, you should have enough that you're able to do that 80-20 or 70-30 split. So the purpose of splitting the data, like I say, is we have 100 observations. We get these 80 observations, and using those random observations, we build a model. We then have a model, but before deploying that model, we don't know how good it is. So we have to test it, and we have to test it knowing the output. So when we did the rabbits and cats and dogs, we know intuitively whether the picture that we're putting in is the rabbit or cat or dog. We know that instantly. But when we're doing this numeric regression modeling, we don't necessarily know what the output will be. So that's why we take some of that data aside and use that to test the model. So we train the model, we build the model using 70 or 80% of the data. Then with the remaining data that hasn't seen the model before, hasn't went near it, has been completely separate, we use that data. It has features and it has outputs, so it has X and Y values. We use that data as a testing subset, so we use that as our testing split. Now we'll run that data through our model and see what Y values our model give out. We'll compare that to the actual Y values of these observations of this testing set to see how accurate and how well our model is working. Does that make sense? I know that's a lot to take in, and it'll make a lot more sense when you see it practically, when you see it working. But basically, we have a set of data, 100 observations. We have all the features and we have all the labels. We have all the inputs and outputs. We take a portion of that away, keep it separate. We build our model, and then we use that data that we've kept separate. We use just the features, run it through our model and see what the outputs our model gives us. Compare those outputs to the actual outputs that were true values, and that's how we assess how good our model is. That's how we test our model. Does that make sense? Because like I say, I know that's very wordy. It's a lot to take in. Okay, just
yeah, I think so.
Yeah, makes sense.
Okay, just shout if you have any questions. Like I say, I'm not assuming anybody, you know, has a maths background or anything like that. So when we plot, if it's only one feature, just one X here, when we plot that, like we see here, a scatter chart that we've seen before. So this dotted line is your function. This is your model. This is your f of x. And these blue circles here are the actual observations. So you can see they're not always on the line, but this line is just the line of best fit. This is the function. Like I said, this is how the model works. And in this case, it's f of x equals 35 plus 1.5x. You don't necessarily need to know that formula. Like I say, we won't be coding or anything like that, but it is good to understand if you have more than one variable. It's good to understand the weightings, you know, how much each variable or each feature, how much that contributes to the output, how much significance that has on the output. So just for reference here, when the formula is written like this, 35 is the y-intercept, and 1.5 is the magnitude, is the gradient of the line. So that might go over some people's heads, but it just means that each time x is increased, for each unit of x that's increased, the function will increase by 1.5 times that. That's all that means. Okay, so you can see here y hat is an estimate. So I've just taken our testing data here and put it in here. And so what we would do, we wouldn't run the model on that y value. We would just, because this is the testing split, we've just put our x values into the model and we're given out an estimate. So anything our model gives us out is a prediction or is an estimate, and that's denoted here as y with a hat on top. So that's our estimate. That's what our model thinks that the actual results will be. Now, when we compare that, because this is historic data and we already have the y values, when we compare that to the y values, we can see how accurate or not our model is then. So that's just an example of when you would use the testing data, the x, y testing data, and you would compare it to what the model output given the x values. And then you just compare the actual y's to the predicted y's, and that tells you how accurate or how good your model is at predicting. So building a regression model in Azure, there's several steps. I've just taken this off Azure, off the portal. But like I say, Microsoft's really good. Their stuff's really good, and I'll actually give you a link for the end of the class that you can work through. But we don't actually have to go on Azure, and we're not using the portal to build our models this year. But it's really good because it breaks down step by step each phase that the machine goes through when building the model. So the first thing that we would do is upload the raw data. So given the raw data set of 100 observations, I think we said 100 observations, we would upload all that raw data. We would select which columns, so that's just which features we want to include in the data. So for the bike rental shop, we said we would include weather data like temperature, like rainfall. We would include location. We would include all these different things. We would include bank holidays, you know, if it was a weekend or a weekday. So we would select which features to use, because sometimes when you're given a massive data set, you don't need all the columns, you don't need all the features, and there's no point in including them if you don't need them. So we select which features we want, and then we clean any missing data. So if you're ever given a large data set and it has missing values, or a value might look completely out of the ordinary, like an anomaly or something like that, it could just be, you know, a typo, something like that. So any missing data, any data that doesn't look quite right, we would always review that and try to clean that. So it's up to you how you clean that. So if it's missing data, you can choose just to remove that entire observation, remove that row. You could choose to just take an average of the other values in that column and just replace that missing value with the average of the other observations for that column. You could choose to replace it with the most common value in that column. So there's several ways that you could clean the data, and that's completely up to yourself. We then normalize the data. So normalizing the data normalizing like a maths term, and it basically means setting your data, putting your data all on the same scale. So if we have something like if we're choosing day of the week for our bike rentals, if we're choosing day of the week and we have Mondays 1, Tuesdays 2, Monday to Sunday 1 till 7, and that's in our data set. If we look then at how many centimetres of rain, and that's logged as 0.1, 0.2, 0.3, you can see there where the model might have some trouble with the weightings of the different features. If one is 10 times the other, then naturally the model will only give a small weighting to the one that has the largest number, but that might still be a significant feature, and we don't want to miss that. So normalizing the data, it's done automatically for us, and it just means putting it all in the same scale, putting the data in the same scale, usually between 0 and 1. So the rainfall, I think if it's between 0.1 and 1, that'll be fine, that'll stay there. But the weekdays, if they're between 1 and 7, that'll go probably Monday is 0.14, Tuesday is 0.28, Wednesday is 0.42. Do you see what I mean? Just to normalize the data, get it all in the same scale, and keep it all uniform, so that then each feature, the weighting of each feature within the model will be accurately shown. And if one feature has a higher weighting, then that means it's more significant. So it's just a really good way for us to know and see clearly, looking at the model, looking at the f of x equals, which features are more significant. So that's why we normalize the data. Then we split the data. So that's for training and testing. So we split the data. So we take, say, 80% of the data and we train that using linear regression. We train that model. Then we use the testing data then to score the model. We use the testing data to score the model and see how accurate the model is. So if our model is working really well and every label that it's output, we've matched it. This will rarely happen, but we've matched it like for like with our Y value, that was the actual value, then our model will be really accurate. We'll be really happy with it. What's more likely to happen is our model is only showing, 60, 70, 80% accuracy, and we want to make our model better. So we can do that by tweaking the features, tweaking the weighting that we're given to each feature, or we could add more observations and let the model kind of adjust itself. So that's basically end to end how we build a regression model. This is in Azure, but this is the process, the standard process for building a regression model. Put in the data, clean the data, normalize the data, train the data, use a testing set to evaluate then how accurate your model is. So before I give you this lab, I'll just quickly go through the evaluation metrics. So these are the main evaluation metrics for regression models. So the first 4 are error terms. They're all between, sorry, they're not all between, these 2 are between 0 and 1. So these are all error terms, and the lower the better, because they're errors, the lower the better. We don't want any errors, so the less the better. The last one is R squared. Now this is the coefficient of determination, and this is probably the most popular metric for evaluating regression models. And the definitions there, it basically just determines what proportion of error is explained by the model. Values between shouldn't, that's nothing there. But the values are between 0 and 1. 1 being better for R squared. R squared, when R squared is 1, it means your model is 100% accurate. If R squared is only like 0.5, if it sits in the middle, then you might as well do a coin flip. Your model's only 50% accurate, so you might as well just leave it up to random guessing. So we always like to see an R squared closer to 1. 1 is like 100% accurate. Mean absolute error, like I say, the lower the better. Root mean squared error. The definitions are basically in the name, the square root of the mean squared difference of the error. So the error is the difference between the predicted value and the actual value. Relative squared error, a relative metric between 0 and 1 based on the square between predicted and true values, the lower the better. Relative absolute error, so relative metric between 0 and 1 based on the absolute differences between predicted and true values. So the lower the better. Like I say, the lower the better for these 4 error metrics. And then for the R² one, then the closer to 1 it is, the better. Okay, so we'll go on to the lab now. So you might have seen, have you used Microsoft Learn materials? Did you use them last year for Azure? Yeah. Okay, so this is just a wee link to Microsoft Learn, the Microsoft Learn path for regression models. You don't have to do the lab, like I say, your subscription in Azure is probably expired now, but Microsoft do explain how the builds of a regression model really well. So have a wee look at that. I'll let you do that now in your own time, and we'll come back at about 12:25. And then we'll just finish off, see if anybody has any questions, and go through what we've covered today. I'll just put this link in the chat as well, just in case anybody doesn't have access to that PowerPoint. So there will be on this learning path, it will refer to the Azure portal, but like I say, don't worry, you won't we won't be using Azure, the Azure portal to build your models. So don't worry about that, but just make sure you kind of understand the theory and step by step how to build a regression model. Okie dokes. So we'll meet back here 25 past. Like I say, I'll be here. Just let me know if you have any questions in the meantime.
Thanks.
Thanks.
Thank you.
Yeah.
Thanks, Sam.
Right, folks, did everybody manage to get through that okay? Like I say, there's a lot there about the Azure portal, but you don't have to really pay any heed to that part of it. It's more just understanding the process of building these models. You know, step by step, what would you do, or how do you go about building a model? Radio, just to recap them, what we went through today. So we covered an introduction to linear regression. So what is linear regression? It's one of the main types of machine learning model. It gives out a numeric value. We looked at features and labels. What's the difference? Features are the X values that go into building the model, and a label is a Y value, or the numeric output that we get back from the model. We looked at testing and training. So we'll split our data set. So our historic data, we split that so we can leave some to the side to test our model later. So we test it using 70 or 80% of the historic data, and then or train it using 70 or 80% of the historic data, and then we'll test it then using the remainder to see how accurate our model is. And we'll evaluate it. So we'll evaluate it using these metrics. We went through the model build, so the flow of what you do. So you import the raw data, you select which features you want, clean any missing data, make the data standardized, split it between training and testing, train it, test it, and evaluate it. And that was it. So next week, we'll continue going through Introduction to Machine Learning. Next week, we'll introduce two new concepts, classification and clustering. These two are more straightforward than linear regression. Like I said, linear regression is probably the most complicated, but it's also the most common, so it's really important to understand. And we'll do some practical lab work. So I know we did the Google ones today, so we'll look at some other sites that we can go on and do some lab work on that, and that'll really help then towards the assignment. So does anybody have any?
Can I ask where we?
Yeah, go ahead.
Can I ask where we find these the PowerPoints?
Yeah, they'll be uploaded to Canvas, and they're on the main teams as well. So if you go on to class materials, so just on this general chat, if you click on files, and then in class materials, all the lecture notes will be uploaded there before the class. And I think there's recordings there as well. If anybody records the class, they'll all be saved there as well.
Okay. Yeah, I think I found it. Thanks very much.
Okay, but they'll be on Canvas as well. Just give me a shout if you can find them.
Okay.
Okay, brilliant. That was a lot to take in today. I know we went through loads of material, so have a read through it. Make sure you understand everything. Let me know if there's any questions at all. We'll do another recap next week, sure, before starting classification and clustering. But yeah, it was a lot to take in. So yeah, just give yourself some time to go through it.
Thank you.
All right, brilliant. Have a great weekend, everybody. See you next week.
Right, see you next week. Cheers.
Okay. Cheers.
Bye.
Bye.
Bye. Bye.
Thank you. Bye.
Cheers, see you later.